Here we'll have a look at 2017, question 9, part B. So this is where something is floating in multiple liquids. Now, if you have a peek at this question, it is an iron cylinder dropped into a big empty cylindrical tank. So to save a little bit of hassle, we're going to draw this as a cross section here. There's my big iron cylinder sitting in there. So, what's the density of the object here is 780 because it's iron. Now we're putting some liquid in. Density of the liquid is mercury, 13.6. So no easy bits and pieces with water here. We add a certain amount of mercury until it begins to float. So it's going to be something like this. All right. Mercury is denser, so I know it doesn't need to go over the top. So at this point, the buoyancy is equal to the weight. That's what just about to float means. So there's no gap underneath it at the moment. We know the total distance here. I'm going to convert to meters. It's 10 centimeters, so it's 0.1 meters. All right. And then this is the distance we are going to try and find. So we'll call that h for the moment. So now our question isn't too bad, really. We've simply got to find an expression for the buoyancy and expression for the weight. Well, let's start with the weight because it's a bit easier. So the weight equals V rho g. That's one of your little standard weight equations. Well, what's it going to be in this case? The weight equals the volume. So remember, the volume of a cylinder equals pi r squared h. It's just your general expression. You should know that off the top of your head. Now, if we just pause for a moment before I lash in and make my life difficult, the buoyancy is going to be the volume displaced. So it's going to be the same radius. So I'm going to look at this as pi r squared, okay, and then 0.1, the height here. That r squared is going to cancel that later on. I could put it in as it's given in the question. I don't need it for the moment though. So the volume with the density, which is 7,800 by g. And we're going to, again, I'm going to leave g as g because I'm going to get an expression for g in the buoyancy as well. So no point in making our life too hard. All right. And so the weight equals 780 pi r squared g. Okay, pi r squared 780 g. Perfect. Do a little double check. And that's one expression. So that one wasn't too bad. Let's look at the buoyancy. So the buoyancy is the volume displaced. Okay, we'll just put this up as the moment. Volume displaced by the density of the liquid by g. So the volume displaced is this little section here. Okay, how do we do that? Well, the volume displaced is simply pi r squared h, because we defined h as the depth of that. By the density of the liquid, 13,600 by g. So you're seeing a lot of our common terms here. Well, we know since buoyancy is the weight, therefore, we'll sub these ones in. Pi r squared h by 13,600 by g equals, there we are, 780 pi r squared g. So it looks a little bit ugly, but that is about to change very rapidly because cancel the pi's, cancel the r squareds, cancel the g's. So in this case, let's see, we'll squeeze it in down here. H equals 780 over 13,600, and that equals, pop this into a little calculator here, 780 divided by 13,600, 0.057. So that is 0.057 meters, which is 5.7 centimeters, which would make sense. It's about half of the total height of the cylinder. So there we go. Part 1 done. So that was a nice, fairly standard part 1. Part 2, they're making us think a little bit more. It gets a little bit trickier. Now, if you have had a look at this on the solutions, you probably have melted your brain trying to figure out what on earth is going on. We'll slow down here and figure it out. All right. The key here is we've added some oil. Okay. But when we add a bit of oil, we are going to have an additional buoyancy force acting on the bit of the block that's submerged. Since it's just about to float, any additional buoyancy force is going to make it float. So our new diagram looks like this. There's my iron. Alright. There's my little line of mercury. And there's my oil. So this is the section with oil in it. This is the section with mercury in it. Now, if we look at our buoyancy is going to be composed of two parts. There's going to be a section which is related to the amount of mercury displaced, and there's going to be a section related to the amount of oil displaced. We don't know how high it's floated, and actually we don't really care, because if we look at the question, we're looking for the volume of oil. So what I'd really like to know is this distance here. Now, to avoid a bit of confusion, I'm going to call that K, all right, as opposed to H, because if I'm using H, it's kind of begin to get a bit head wrecking. All right, well, it's floating, it's in steady state, so the buoyancy equals the weight. I know what the weight is. The weight of the block hasn't changed. That's it over here, 780 pi r squared g. Again, we'll leave it in r squares and g's. We'll see if any of them cancel out. So, what's the buoyancy? Well, the buoyancy comes from two parts. One is the part in the oil. So let's look at that one first. So remember, buoyancy is always the volume displaced by the density of the liquid by g. So in this case, the volume displaced is pi r squared k. All right. Pi r squared k. That's the volume of this guy here. Multiplied by, put this in brackets, keep it tidy, the density of the oil. Well, that one, we look back to the question, we'll see it is 1030 by g. Plus, we're also going to get a contribution from this little bit down here. So, what is this? Well, we know the total distance is 0.1. You can see that there. So, it's pi r squared 0.1 minus k. All right. By the density of the mercury, 13,600 by g. A little bit uglier, but not the end of the world. So, let's lay the whole thing out. We have all of that equals the weight. So, we might just tidy this section up a small bit here. So, we have pi r squared k by 1030 by g plus, we'll leave it the way it is for the moment, because I am not bothered writing all that out, because I know a load of this is going to cancel and it's going to get a bit simpler. 13,600 g equals, you could have put it there, but I'm being nice and tidy for you guys, equals the weight, equals 780 pi r squared g. So that's just basically buoyancy equals weight. That's all we're doing here. Now, cancel to make this our life nice. We can use a pi. We just make sure there's in each expression before we go too mad. We have an r squared in each expression, and we have a g. Fabulous. What have we got left? 1030 plus 0.1 minus k by 13,600 equals 780. All right, I like this. My only variable is k. I've lost a k there. Whoops, the daisies. There we go. That's why we write this out. So this is solvable. Just double check. Got those ones. Got that. Got that. All right. I'm going to expand this expression here. So 1030k plus 1360. Okay. Okay, is this side? Actually, well, I'm going to do a little bit of a cheeky trick here, because I'm going to change all of the signs. There we go. Save me just going over that one. So that ends up with 13,600 minus 1030, which is 12,570, okay, and that is minus 780. Bring this guy over, comes plus, so it's 1360 minus 780, 580. So k equals 580 divided by 12570, and that is 0.046 meters, which again is about what I'd expect, because it's a fraction of the 0.1 meters. So the 10 centimeters, this is 4.6 centimeters. Now, that's not what we were asked though, is it? We're not quite out of the woods yet. We are asked for the volume of oil required. Well, let's think of the volume of oil. It's kind of weird, because if we look at it in 3D, it's really this little section here. It's kind of missing this interior slice. So we need to look at it's basically the volume of a big cylinder minus the volume of a little cylinder. So what's the volume of the big cylinder? The volume of the big cylinder is pi. We'll leave that as a pi. What's my outer radius? This guy here is 0.15. Diameter is 30 centimeters. So radius is 0.15. And the little one here, the radius equals 0.25 over 2, so that's 0.125. So just lay this stuff out clearly, because this is a great way to make small mistakes. Okay, pi by 0.15 squared by k, 0.046 minus pi 125 squared, 0.46. So I'll leave the pi outside for the moment, and I get 0.15 squared by 0.046. Okay, 0.125 squared. All right, now you can actually store these guys, so I'm going to store that into C. So I am going to get 0.001035, should have stored this earlier, but I forgot, minus or equals C, and that is going to be that by pi equals that. So my volume here is 0.000994, three significant figures, meters cubed, and we just tidy that up a little bit, of course. So volume, we can hop this back if you want. 1, 2, 3, 4. There we are. 9.94 by 10 to the minus 4 meters cubed. That's my volume of oil.